Hello students, welcome back. This is gonna be the fourth and the last video in section 1, I hope. I really hope to complete it in one video. The next example is fast modular exponentiation. We're gonna talk about some computational methods to calculate some humongous exponentiation like this, or even worse like that. And the foundation for this is right here. If the bases are congruent, then so are the powers, as long as we have the same positive integer power, k. The reason is because we can just repeat the congruence of this modular arithmetic, especially the multiplication part, infinitely many times. Just repeat it k times, basically. The base case is just straight ahead multiplication, which we covered already in 1.3, and then apply the inductive hypothesis. That's a sketch. The detail is left to the students. A remark though, the bases are congruent, then so are the powers. If the exponents are congruent, then what? In that case, the answer is no, you can't do that. The exponents here, the powers, those are coming from the counting, not from the congruence or anything like that. For example, 6 and 1 are congruent modulo 5, but 2 to the 6th power and 2 to the 1st power are not congruent modulo 5. 2 to the 6th power is 64, which is congruent to 4 modulo 5. 2 to the 1st power is, of course, just 2, and 4 and 2 are different modulo 5. There are many other examples, but that's sufficient. Now let's go ahead and use those. In this kind of computation, let's see, 2 to the 20th power. Is there any way to reduce the base 2 modulo 41? Doesn't look so promising because 2 is less than 41, but I can reduce it like this, 2 to the 2nd power to the 10th power like this. 2 to the 2nd power is 4, and can I reduce 4 modulo 41? No, not really, I can't do that. That's too small, so let's do it this way. 4th power and then 5th power. 4th power is 16. Can I reduce 16 modulo 41? No, not really. Still, too small is meaningless, so let's do it this way. 5th power to the 4th power. So we have 32 to the 4th power. Now, does it make sense? This time it does, because 32 is reasonably close to 41. That's what you're going to get. Negative 9 to the 4th power. Negative 9 squared is positive 81, right? So this is positive 81 squared. And 81 is congruent to negative 1 modulo 41. So this is 1. Modulo 41. 41 times 2 is 82. So 81 is congruent to negative 1. Let's see. Mod 2 to the 20th power 41. And what's the remainder? The remainder is 1. Okay, this computation is correct. What did I do in my answer key? Yeah, very same. How about the next example? Whoa, this one looks really bad. 2 to the 644th power. By the way, don't do this. 2 to the 644 is congruent to 2 to the negative 1st power modulo 645. This is not true. This is not true in general. You cannot apply modular operation to the exponents. You can do that only to the base, and let's get those bases. 2 and then 2 squared is 4, still too small, so square it again, 2 to the 4th power, that's 16, still too small, square it again, 256, still too small, square it again, and then we have 2 to the 16th power. Finally, that exceeds 645, so we need to do some reduction. Divide 60,536 by 645 and take the remainder. We get 391. Alright, now square it again. 2 to the 32nd power is 391 squared, so we have this number, and then eventually get down to 16 modulo 645. Okay, does it help? Well, haven't you seen this 16 before? Yes, you have seen it right here. 2 to the 4th power. And then this one, 2 to the 32nd power. So that tells me 2 to the 32nd power is congruent to 2 to the 4th power modulo 645. So we can apply this reduction in a place that we can use this reduction here and there, and hopefully this can reduce this humongous exponential. Okay, how can we reduce that? Well, one way to do that is to use the division algorithm, so let's try that. So 644 divided by 32, 20 point something, so 644 is 20 times 32 plus some remainder, so remainder is 4. Alright, so we get this. 2 to the 644 can be written as 2 to the 20 times 32 plus 4, 2 to the 32nd power to the 20th power times 2 to the 4th power. How's that? And then that can be reduced to 2 to the 4th power to the 20th power, 4th power, and that's the same as 2 to the 4th power to the 21st power. To the 84. Did I do this right? Okay, so far, doing this and then that was pretty hard. Well, no, not really. You could use long division. So given time, in a couple of minutes, you can do these. And then getting this 20 as a quotient and remainder 4. Again, using long division, you can do that. So nothing really outrageous took place to get down to 2 to the 84th power. 84th power, let's see, I can reduce it further down to division by 32, yeah? So 84, 2 times something, so 2 times 32, okay, 20. So we are going to get that. 2 to the 644 power is down to 2 to the 84 power, and this is 2 to the 32 power, second power, times 2 to the 20th power. Is that right? Did I skip too many steps? 2 to the 2 times 32 plus 20 quotient divisor remainder. So this is congruent to 2 to the 4th power squared 2 to the 20th power, and this is turning out to be 28th power. Okay, 644 power is down to 28th power. 28th power is not impossible, we can do it, but is there a cleverer way to reduce it further? Okay, that's down to 2 to the 28th power. So that's, let's see, among those numbers that showed up, 16 power and 28 minus 16, we have 12 power, right? But 12 power is 8 power, 4th power, all right, we got it. 16 power, which is 391, 8th power, 256, and the 4th power, 16. So this is 391, and then 256, and then 16. Looks like finally we got to a point that we cannot get away. 16, 8, 4, they're all very low compared with 645, and then they all appeared. So yeah, go ahead and do this computation, and if you do it, what do you get? You're supposed to get 1. I use a little bit different method here. Looks like this is textbook's method. 64 power, 128 power, keep squaring, and then we go back to 391, and then 256 power back to 16, and then we have a loop. That's why we use division algorithm to bring everything down up to modulus 32. So we can bring those down to 512 power, 132 power, 512, 128, 4th power. You got that. Well, either way it works, but I like the second method a little bit better with division algorithm and stuff. In the end, you cannot get away from this computation, and that turns out to be congruent to 1. Okay, alright, so much for that example. Very computation heavy. Let me comment on the last one here. If you have a systems of congruence, different moduli, mod M1, mod M2, mod M3, and so on up to mod Mk, then A and B are congruent to mod L, where L is the LCM. The difference between the two, left-hand side minus right-hand side, A minus B, must be divisible by M1, M2, M3, all the way up to Mk. Therefore, it is congruent to, it is divisible by the LCM. So the difference, they're all divisible by Mi. So that's the same as divisible by the LCM. How many of those systems of congruences are we going to see here with different moduli? We'll have to do Chinese remainder theorem later, so we may have to use it, but all those are special cases when they're all relatively prime. In that case, just multiplying them all. So the LCM case is pretty rare, I have to say, but that's the general result. Anyway, that concludes section 1, and let's begin section 2 in a separate video.